Let's have a look at another problem on the. This is where actually we're talking about involving phase change of between benzene and toluene. Okay, so benzene and toluene at 10 degrees Celsius is fed continuously to a vessel in which the mixture is heated to 50 degrees Celsius, and the liquid product is 40 mole percent of benzene, and the vapor product is 68.4 mole percent of benzene. The operating pressure for the evaporator is 35 millimeter mercury. How much heat must be transferred to the mixture per gram mole of feed? Okay, so now we have a problem such that um, we are actually having a phase change, okay, because when we mention equimolar liquid mixture, so which means that we have 50-50, 50% of benzene and 50% of toluene, okay, and then it is heated to 50 degrees Celsius. So we have a mixer, and then there is 50% benzene and 50% toluene, and then there is it is heated. So mixer is heated. Then we have two side product, which is one it is in a vapor state and another one is in liquid state. So the liquid product is 40 mole percent B. So you have 40 mole percent B here, 40% of B. So supposedly you have 60% of T. This make more sense. Why is that? Because benzene has a lower boiling point compared to toluene. So you should have more toluene in the bottom product, which is in the liquid product. And in the vapor state, you have actually, they said you have 68.4 more percent B. Okay. And of course, the remaining of it, so it's 100% minus 68.4, which is 31.6, should be toluene. Okay. And then the pressure for evaporator, this is 35 millimeter mercury. So how much heat must be transferred? So first of all, we need to draw the flow chart. So we have a flow chart such a way that as I have drawn earlier. So things coming in at 10 degrees Celsius, and then what is going out is actually at 50 degrees Celsius, 35 millimeter mercury with these particular values. Okay, so similarly at the bottom product is also at 50 degrees Celsius and 0.4 and 0.6 benzene and toluene respectively. So our basis of calculation, we choose just 1 mole of feed. Okay, so we know that this is 1 mole and this is certain number of mole, and a liquid is also something that we didn't know. So we must need to solve the mass balance first. Okay, so we need to carry out the material balance to determine the unknown step. So we know that total mass balance is 1 mole equals to NB plus NI. So this is one equation. Another equation, we can use benzene or toluene balance. So once we solve this, we're able to determine what will be the molar flow rate in the vapor state as well as molar flow rate in the liquid state. And the next thing is actually we write the energy balance. We know that this is an open system, okay, because this is not a closed system. Why is that? We know that what is coming in is in term of the rate, okay, and we know that there is no assuming kinetic and potential energy plus both equals to 0, and then now it is left only with H, okay. And why this is H? Because it is an open system, so we straight away we know that we need to calculate H instead of U, and we need to determine what will be the reference state and determine the H. So in this case, we can choose a reference state because we have two components, toluene and benzene. And toluene and benzene, we have two states. One is at actually 10 degrees Celsius. Another one is at 50 degrees Celsius. And actually at 50 degrees Celsius, we either have liquid or vapor. And at 10 degrees Celsius is actually liquid. So we need to pick up what will be the best reference state for us. So in this case, maybe the best one is actually we pick up toluene at liquid state at 10 degrees Celsius, as well as benzene at liquid state at 10 degrees Celsius. So you have to know that different component has a different reference state. Yes, but then we need, of course, towards the end, we're going to combine this together. So we could not determine delta H because there is no tabulated data value available. Right. So the next thing to do is actually we need to construct inlet and outlet table. When we know that the reference state is at liquid, benzene is at 10 degrees Celsius 180 m, and similarly for toluene, which is liquid at 10 degrees Celsius 180 m. So this is where actually we start to draw the inlet outlet enthalpy table. So what is coming in is actually 0.5 mole of benzene in liquid state and 0.5 mole of toluene at liquid state. So because this is our reference state for both component, so delta H value is straight away equals to 0. And from the our material balance, we have determined this is the component value for vapor and the liquid state for both benzene and toluene. So this is where actually we label as H1, H2, H3, and H4. So next thing is actually how do we determine the value of H1, H2, H3, and H4. Okay. So what is mentioned here is that the reference state is conditioned at 180 m, but there is no pressure available for feed stream. Therefore, anything got to do with the changes of pressure, okay, V delta P is equals to 0, which is negligible. Uh, the process which is run at low temperature or high pressure, we can neglect the pressure effect on enthalpy for solving H1 to H4. Okay, which is not at unusually low temperature or high pressure, which is, for example, if let's say it is somehow got to do with ideal gas, so we can just simply neglect the effect of pressure. So any term with V delta P, we can just simply neglect it. And this is where actually we solve for specific enthalpy. So first of all, we need to draw the hypothetical process path. So imagine for H1 just now, we are talking about, let's have a look here. For H1 is actually, what is that? Okay, H1 is got to do with benzene, but now which is still liquid, benzene in liquid form, which is going out at the bottom outlet. Okay, so there is no change of um, temperature, there is no change in terms of the phase. But first of all, we need to know what will be the boiling point for benzene and toluene. So we could be very careful on that. So here, because the benzene is actually changing from 10 degrees Celsius in liquid to 50 degrees Celsius in liquid, so there is no change of phase, and there is no change of and the effect of changing of pressure is negligible, okay, because it's very small amount. If you minus the pressure changes, it's very small. So you can have like from here 10 degrees to 50 degrees Celsius is just a calculation of CPDT, okay, which is from 10 to 50. That's all. So if you refer to table B2, then you'll be able to get all these coefficient, substitute into it, and do perform the calculation, then you'll be able to get your delta H1. Similarly, for your delta H2, which is respective to toluene, which is also you take the reference state at 10 degrees Celsius and in liquid state, it also changed to 50 degrees Celsius and liquid state. So again, you can do the CPDT from 10 to 50, but of course, the CPDT value inside here is different because you need to refer to table B2. Okay, then you will get the coefficient of A, B, C, etc. in table B2, substitute into it, and then you'll be able to get your delta H2. So that is quite straightforward in it. Okay, so this is what I've given to you. But the next thing is actually you need to calculate your delta H3. So remember that delta H3 is now your benzene which is at vapor, and it is at 50 degrees Celsius. Okay. And then this is at 35 millimeter mercury. Again, the effect of temperature changes, pressure changes, we can neglect. So what we have to do is actually we need to draw the hypothetical process path, which is actually from the change of temperature from 10 degree to the boiling point, and then from the phase changes from the liquid to become vapor, and then there is another change which is from the boiling point to 50 degrees Celsius. So that is actually um, this is actually the hypothetical process path that you have drawn. So the hypothetical process path that you have drawn, this is where actually you substitute the value. So for example here, for your benzene, okay, the boiling point is at 80.1 degrees Celsius. So you can do the CPDT, which is represented here. And then for phase changes, you can take the latent heat of vaporization at 80 degree. And the next one is actually the changes from 80 degree to 50 degrees Celsius in terms of vapor state. So whenever that you calculate this, you can substitute the information, and then you'll be able to determine your delta H3. You can repeat the similar procedure for toluene, subject to that the changes of temperature right now is from 10 degrees Celsius to the boiling point of toluene. Okay, so here the boiling point of toluene is 110.62, and similar procedure here, then you should be able to get all these values necessary from table B2, and you have to remember exactly that this is CPDT for liquid and this is CPDT for vapor. So when you substitute everything, then you'll be able to get your delta H4. So whenever that you got all this value, you have to substitute back in the table. Okay, you remember the table that I have shown to you earlier. So this is a table. So when you fill up all this information, you have to make sure that this particular value multiply with this, add together with this, multiply with this, and so on. And because this is the product of this is 0, so you'll be able to determine that delta H out minus delta H in. Okay, so you can follow this calculation, because this one, it is resulted in 0. Why is it 0? Because we have chosen both components reference state at the inlet part, so the enthalpy is 0, so the product of it is 0. Then you just need to calculate the product between NI out, summation of the enthalpy out, multiply all of this together, then you'll be able to get the Q value at 17.7 kilojoule. Okay, kilojoule is supposed to be kilojoule per second. So you got the actually the power of this. Right. So I think that's all that I want to show you in terms of the example how to perform energy balance for non-reactive system. So you have learned about hypothetical path as well as the phase change. I hope that you could do on your own, try to refer to the textbooks, and then try to understand how you can improve your understanding further by doing some kind of examples in the textbook, and try to recall this again, how can you actually solve this particular problem. So that's all for now. Thank you very much, and see you in the next video. Assalamualaikum warahmatullahi wabarakatuh.